All right, so thanks very much for having me. I'm Justin from Singapore, and thanks very much to James and Ankit for inviting me. I wasn't expecting it, but they asked me to give a tutorial on frontiers. I don't really know what this means. What I'd like to do in the tutorials section is basically just kind of give you a little bit of a it's a bit hard to define what a tutorial in frontiers is. I think I'd like to pose some questions, but I'd like to kind of show you how I get to the questions. In this tutorial part, I'd like to basically first observe that in the last couple of days, we've basically seen like a lot of various strategies for doing out of equilibrium engineering. So I think there are maybe three broadish kind of things if you kind of take these words here in the broadest possible terms. In particular, there's one which is to exploit the sensitivity of band structure to some kind of periodic drive, some kind of Floquet kind of stuff. So this could be, there you see Floquet band structure engineering, but it could be like a lot of more things as well. One other thing that we heard a lot about was kind of exploiting the sensitivity of material responses to the out of equilibrium distribution function. So for instance, yesterday we heard from Claudia about injection currents and photocurrents. And so this is a kind of way of being kind of sensitive to look at responses such as current that are sensitive to the out of equilibrium distribution function. So if you can morph how the out of equilibrium distribution function looks like, we should get some kind of interesting responses. And maybe the third thing we've heard all throughout this week, day 1, day 2, day 3, a little bit from Andy, a little bit from Ankit, a bit from everything, whereby you kind of drive or you design collective modes of either photons or phonons or something else, and you use that to morph the response of acorn material, right? So we just try and make sure that we kind of understand what I actually mean here. So in this particular strategy of kind of exploiting sensitivity of band structure to your periodic drive, we heard a lot yesterday from Martin that the interaction of light and matter is quite sensitive to quantum geometry. And let me just try and just bring this home and quite clearly. And the reason for this, I think, as Martin already pointed out, is that we have these dipole matrix elements, right? There's in the long wavelength limit, light and matter kind of interact through a dipole interaction, and these dipole matrix elements are these R's here, all right? And so this is kind of a transition between a band N and a band M. It turns out that these dipole matrix elements R, M, N here are actually the basis for quantum geometry, right? So for instance, the Berry curvature in band N, right, is defined in terms of these products of these dipole matrix elements. Of course, you need to sum across all bands that are not N, but the Berry curvature in band N is determined by your dipole matrix elements, right? The same thing goes with the quantum metric as well. So while the Berry curvature is the antisymmetric combination of these dipole matrix elements, all right, the quantum metric is the symmetric symmetric contribution of these products of dipole matrix elements. All right, so as you can see here already, that the geometry of the system determined is intricately intertwined with actually the regular optical transition matrix elements that we all know and love. So that's the first thing. So geometry plays a huge role in optical transitions, and you can even try to make this a bit more rigorous, right? So recently, so lots of people like to use this to kind of say that optical transitions and and band geometry are one-to-one correspondent, and everything. But it turns out that you really need to sum across all bands here. So in very simplistic systems, in two-band systems, the mapping is very nice, but then it fails beyond these two-band systems. You can't really say that these optical matrix elements are exactly equal to the Berry curvature of a single band anymore if you're beyond a two-band system. It turns out that you can do a little better than that. So Ashvin recently wrote a paper basically saying that you could actually define some kind of Riemannian space where these tangent vectors are actually determined by particular by these states here, right? So we can create some kind of weird manifold, and actually it turns out that this manifold actually allows you to describe optical transitions really in a geometrical way, and so this tries to make this kind of this analogy between quantum geometry and optical transitions a bit more exact. So that's that. But we also know that light-matter coupling also determines quantum geometry, right? So we all know and love this kind of proposal from Oka and Aoki, whereby you shine circularly polarized light on graphene and you open up a gap. And let me just remind you I'm sure you all know this. This basically arises because there's a pseudo-spin kind of degree of freedom in graphene, all right? And basically, when you're looking for the stroboscopic kind of average of this Hamiltonian, right? So the key point, the key reason why there's this opening of band gap here, all right, is because actually the Hamiltonian at one time does not commute with the Hamiltonian at the next time, all right? That's why you get this, sigma z that opens up here, and you can convince yourself that this works, just by just looking at this time-ordered evolution operator and just using the BCH identity. Right, so you can see a sigma x and sigma y here will give me a sigma z, and that just opens things up, right? But the reason why I want to bring this up here is that it's important that there was a pseudo-spin degree of freedom, right? So if my light-matter coupling didn't couple this way here, let's say I had some kind of trivial band insulator, and I applied circularly polarized light, and had no kind of spinner type of thing, you wouldn't get this kind of thing opening up here, right? So the light matter coupling here determines the quantum geometry as well, right? So I've just flipped the words. Geometry determines optical transitions. I've just flipped it around. Light matter coupling determines geometry. All right. So they're very interlinked. So there are these two concepts. So we also know that polaritons, like plasmons, for example, couple very strongly with light. And you can really compress these polaritons down to very, very small mode volumes. For example, plasmons can really go down to very, very small footprints. You can bring it down to footprints of as low as a factor of 1 billion, all right, from that of free space. And at that point, then you can question, do I have this dipole approximation anymore? Right. In particular, one frontier, so I'm trying to motivate this new frontier, is what happens when the wavelength of light is dramatically reduced, right? Whether it be from a polariton kind of point of view, whereby you use you put your quantum material or whatever thing in some kind of heterostructure that really kind of compresses light down. So, or you can use a cavity, or you use some other means. Right, because the key point is I'm going away from this dipole interaction, light-matter interaction kind of thing, where my free space wavelength is much larger than, say, the electron wavelength. But now, if I use plasmons or polaritons or something like that, I might start to now activate higher multipolar interactions. So how would, for instance, the Floquet type pictures that I just showed you, or how would, for instance, the optical transitions, which had a very strong relationship with the dipole matrix element, change? And so that's a question I think that is being addressed. Some small answers have been thought about them. So some people, for instance, this is a work from Marin Soyocic that shows that when I put an atom on top of, say, some plasmonic platform here, I can really enhance forbidden transitions. So these forbidden transitions, they go by En, which are higher than 1, will basically go from, like, say, from P to S orbitals, D to S orbitals. They're typically kind of suppressed in usual free space, but if you put them close, if you put this atom close to a plasmonic platform, there's a dramatic increase of their transition rates. One other thing that can happen also is that you can also use kind of the finite momentum of say, light or polariton to kind of do drag. And so here, this is a proposal from our group, whereby we say that if we have to have both energy momentum conservation with the polariton coming in, and if you kind of tune your light so much so that your Fermi surface is just down here, and this is the surface that conserves both energy and momentum, it turns out that if the surface that conserves energy and momentum just dips just below the Fermi surface here, you can just excite just a small amount of, a small region of phase space around your Fermi surface. So it's a kind of photocurrent R pairs without actually having to use R pairs, right? And you just rely on energy momentum conservation, and the fact that you can tune your Fermi energy in many of these 2D materials, such as graphene or bilayer graphene or something like that. And if you do that, then some of these photocurrents can now be tuned as a function of oblique incidence angle. And so here this shows the injection photocurrent along the X and Y direction that is done in a drag way. And this is the quantum-metric dipole, basically quantum-metric times the velocity in those directions. And you can see that they're quite similar to each other. So this gives you actually a way of kind of mapping out in a momentum selective way your quantum geometry of this system. So some people have started to think about trying to use this higher order and Q kind of stuff. Okay, so that's one frontier. One, at least in my opinion. So some other strategies that we've kind of seen already from this week were for instance, exploiting the sensitivity of a material to out of equilibrium distribution function. All right, so one good example of such a response that is very, very, very sensitive to out of equilibrium distribution functions are photocurrent, rectified photocurrents. And then the reason for this is because the photocurrent that eventually gets to, say, a contact is highly sensitive to the entire photoexcitation cascade, right? From absorption to relaxation to current collection. There are many, many scattering processes and things which kind of go into it. So any small change in the distribution function can inevitably influence what you collect at contacts. And so photocurrent is actually quite a very nice diagnostic of this of the way you push a system out of equilibrium. All right, and we've already seen this yesterday. So yesterday, Claudia talked a little bit about injection photocurrents, and injection photocurrent is quite simple. All there is you have an interband transition rate from the valence band to the conduction band, and you say, okay, fine, there's a change in the velocity of my electron from valence to conduction band. All right, so this is per second. Delta is velocity. All right, so velocity per second times E is a change in current. All right, so that's a change in time and current. All right, so that's why it's injection photocurrent. And as I told you, these interband matrix elements kind of form the basis of quantum geometry, right? So that's why when I shine circularly polarized light, I straight away get Rx and Ry. That gives me Berry curvature. Berry curvature times the velocity gives you something like a Berry curvature dipole. And when I integrate it throughout in, say, a Weil semi-metal around the Weil node, it turns out this gives you a Chern flux around the Weil node. And this is the reason why in a simple two-band model, all right, I will get this kind of quantized photogalvanic effect. Right, so it's this, but the key point here is that you're using light here and your optical selection rules to kind of selectively select particular parts of your distribution function to excite, so much so that you get a very highly out of equilibrium distribution function that can pick up different velocities on different sides of your Brillouin zone. All right, so that's kind of a prototypical example of how the outer Coulomb distribution function can change a photocurrent kind of measurement. So that's just one of a diversity of second-order nonlinear rectified photocurrents. There are actually very many, as you can see here. And all of them probe different aspects of this out-of-equilibrium distribution function. So for instance, the injection photocurrent basically tells you about this kind of photoinduced velocity difference. It actually corresponds to the diagonal of the second-order nonlinear density matrix. Whereas the shift photocurrent, tells you about the shift of, of electrons as they get promoted from the valence band to the conduction band. And, from a technical perspective, this tells you something about the off-diagonal, the resonant off-diagonal component of the second-order nonlinear density matrix. So of course, there are other currents as well. There's been actually a fair amount of interest in so-called metallic photocurrents. And these photocurrents are the ones which are sensitive to stuff at the Fermi surface. All right, so perhaps the most famous is this Berry curvature dipole nonlinear transport. All right, that gives you a kind of a Berry curvature dipole nonlinear Hall effect. But in addition to this Berry curvature dipole nonlinear Hall effect, there's also, for instance, from extrinsic scattering, you can change the distribution function as well of the Fermi surface, just kind of changing that distribution function. This can give you also new kinds of nonlinearities, and there are also these newfangled intrinsic Fermi surface effects, like the ones you've heard yesterday from Su Yang, who told you about quantum metric dipole kind of mediated nonlinear Hall effect. That was intrinsic. These technically arise from off-resonant contributions to the second-order density matrix. So that's that. All right, maybe I'm taking a bit too much time talking about all these, but anyway, I'll just move along. But one big frontier is what happens at strong coupling, and how are the electrons actually distributed? Actually, all these things I just told you about, we're basically just looking at how the density matrices just changed upon excitation. Didn't really care about stuff after that. They didn't really care about how the phonons would relax the distribution function downwards. There was no discussion of any of that, and it become as we know, the out-of-equilibrium distribution function really changes responses, right? So one big frontier is how the electrons actually distributed, what happens at strong coupling. And to kind of drive this point home, let me just look again at the injection photocurrent. So again, we know that the injection photocurrent, goes, at least the circular injection photocurrent goes like this times some kind of coefficient beta in a Weil semimetal, and it multiplies by tau. So it increases as tau or divided by gamma. All right? So this is kind of a weak perturbative limit of this thing. But what happens now when I go to strong coupling, when my electric field is pushed very, very high? What happens there? Well, it turns out that this is the weak part here. It goes up to 1. All right? But if I go to very strong coupling, when my electric fields are very large, it no longer hits this green curve here. It goes downwards, right? So you're already far away from this kind of ideal kind of weak perturbative limit. In fact, actually, you'll find that the injection current will scale as electric field, even though it's a rectified effect. It's kind of a weird thing. It turns out that there are these Rabi regimes where when you push light things into the strong light matter interaction limit, you basically find this kind of replacement. But other things can happen as well. For instance, you can have something called rectification in the optical gap. All right, so typically, I think that if I have a metal, I have an optical absorption kind of Juda peak. So this is the real part of my optical absorption, all right? And it actually diminishes when my scattering rate becomes very small, right? So basically, my Juda peak becomes sharper and sharper and sharper, all right? But if I look at, say, the Berry curvature dipole nonlinear Hall effect, all right? I look at the current here, okay? This is the susceptibility tensor. Sorry, this is the current. This part here is the susceptibility tensor. If I take, for instance, the tau goes to infinity limit, the very large tau limit, I find actually it becomes independent of tau. That's the first thing. And it's pure imaginary. This means that this means that I could get a completely intrinsic photocurrent if I shine circularly polarized light. Importantly, as tau goes away, tau goes to infinity, for instance, it does not change. All right? So I can send tau to infinity, or either sending tau to infinity, the same thing as gamma goes to 0. All right? So my Judo absorption goes down, but I still get a rectified photocurrent. That should sound really odd. It's like optical rectification in the gap of this system. The first question you should ask is, what about energy harvesting and energy conservation? If I have no absorption, how can I ever have a photocurrent there? Because then I could apply an electric field and generate power. What would happen there? So it turns out that this same tensor also gives you an electro-optic effect. So this didn't have to be E omega, E omega. It could have been E omega. So there's a Pockels effect that goes on, all right? A Pockels effect. It changes the real part of the conductivity so much that when I apply an EDC to try to generate some power from the rectified photocurrent, I also create some additional absorption as well. And these two things will compensate each other. And it turns out this actually gives you very high efficiency for this energy harvesting unit at low frequency. So if you want more information about this particular kind of thermodynamic argument, it's in this first paper here. In the same way, it turns out by using this electro-optic effect, it's a metallic electro-optic effect. Most electro-optic effects are in insulators. You can actually apply this EDC, and because an electro-optic effect that it's Pockels effect, it's linear with E, right? So if I apply large enough E in the wrong direction, I can actually change sigma to negative. This would mean that it becomes an amplifier. So it means it would have circularly polarized light coming in. If I shine if I shine circularly polarized light coming in, and I apply an electric field, I should be able to enhance it. So so apply electric field, I should be able to enhance the circularly polarized light. So this would be kind of in the Territz regime, in the metallic regime, how you get an amplifier. And all these things are very interesting, but they still also critically depend on the outer equilibrium distribution function. So that's why I think a frontier really is understanding how the outer equilibrium distribution function looks like. All right, and the last kind of frontier that we have is exploiting the ability to kind of design and drive these collective modes to morph the responses of quantum materials. And they're this rich tapestry of collective modes, the so-called polariton panorama, and all sorts of things, plasmons, phonons, everything, right? And if you drive these kind of things, I couldn't find the very nice picture that Dimitri has. He has this he has this updated version of it, and it somehow didn't load on my computer. He has this big thing. It's wonderful, but I couldn't find it. I was going to show it, but anyway. So as we heard already, or from Ankit's work, if you kind of drive SCO, you can you can make it a ferroelectric. You can put things into metastable states. So that's one paradigm that we have. We drive a collective mode. We try and get some kind of symmetry broken phase. That's nice. But one frontier that I think would be very exciting beyond this, is already very exciting, is if you could intertwine the phase of matter and light itself, or the phase of light, or the order of light, or something, right? And one kind of chief example and kind of very nice example of this is, of course, the superradiant phase, right? Phase transition. And so let me just quickly tell you what it is, and then I might dash your hopes in just a second. But let me just tell you what it is first, okay? So basically what it is you say there's some electronic Hamiltonian. All right, there's some photon here, and there's some coupling between electrons and photon. All right, and the idea is because they're coupled. All right, if I take a mean field kind of spirit, right, and I say, okay, fine, can I generate some vector potential, because this is like a vector potential, right? So if I take expectation value here, this is like vector potential. All right, so if I generate some kind of vector potential, can I lower the energy of the entire composite system of both photon and electron? I can spontaneously generate a vector potential in my system, and I can also maybe kind of stabilize some phase. And this is a very nice paper from Maza and Georges that says that if I put some kind of excitonic insulator inside a cavity, I might be able to enlarge the portion whereby I will have an excitonic insulator. And they call this a super-radiant excitonic insulator. Wow, very nice, right? Because this would be, the phase of matter, excitonic insulator, is intertwined with phase of light. Light, spontaneous vector potential generation, right? So that means they're intertwined. Be very, very nice. Unfortunately, it turns out quite quickly after that, people said, oh, because of gauge invariance issues, one has to be very, very careful. The way you include the diamagnetic term has to be, super clear. And two papers very quickly after they posted came out to say some very strong words about this. And so I would encourage you to think quite carefully when you're doing these kind of things. But it's still a very nice idea, right? It would be great to have some kind of intertwined phase of light and matter. All right, so here are the three frontiers, which I think, I think are frontiers. All right, I'd like to talk a little bit about two of them. All right, in the rest of my talk. But if there are questions now, I'd be happy to take them. Yeah.
I could probably save this for later. But
Okay.
I'm just wondering if there's something very special about measuring photocurrent, because I understood, for example, an injection photocurrent, you generate this current. But I can also detect the current because it's an oscillating current, so it should emit some electromagnetic field. Is this kind of, will give me the same information? Or?
Yeah. Yeah, the main reason why I looked at photocurrent was not because it's the only example, but it's a very kind of prominent example of a response that is very sensitive to the outer equilibrium distribution function, right? So I said, okay, that one thing we're looking at is outer equilibrium things. So if you're going to be engineering the distribution function, let's look at something that's very sensitive to the distribution function. Yeah. Right. So that's the end of the tutorial part. Very good. So I will try to convince you that there is something here in part 3. So you can ask me after again if you don't believe me after that. But yeah, more questions. But very good question, yes. OK, very good. So I have maybe 20 minutes, maybe 25 minutes, something like that. Yeah. So maybe I'll go a little bit fast. I just want to, I'll be using one word a fair amount, and it's non-reciprocity. So I just want to make sure that everyone knows what non-reciprocity is. Basically, it's the ability to discriminate between forward and backward. All right. So here in this case here, if I have something which is going in A1 direction, B2 will come out. Right. But A2 going in this direction, B1 does not come out. Okay, so that's just what non-reciprocity is. Now I'll skip a couple of slides because I'm running a bit late. So the thing I wanted to say was, we're very interested in how quantum geometry changes things, and I'd like to show you actually what happens when you include a little bit of this kind of quantum. I'd like to answer the question, what quantum geometric quantity relates to you when you try to go to beyond the dipole approximation. Right, so that's a question I'd like to answer. And let me say very quickly that we've heard a lot about topology and quantum geometry. One way of trying to understand quantum geometry is to look at the spatial structure of the wave packet. And let me just try to convince you quite quickly about this. So if I try to create a wave packet, for instance, in free space, all right, I can create a wave packet in free space just as a superposition of plane waves. Right, but if I take those same superpositions, all right, the same superposition factors, and in front of the plane waves, and now I tag them onto block waves now as well. All right, it turns out that what happens is that the center of this wave packet now will shift. And it shifts by a barrier connection. And in fact, actually, it's this shift by this barrier connection which actually gives you a lot of a fair amount of the anomalous dynamics. For instance, you can ask, where does this anomalous velocity come from? Right, the anomalous velocity basically comes from the fact that when I apply an electric field, P changes as a function of time. There's P dot. Right, so then if I take, that means I need to take a derivative of my barrier connection here, which actually will give me this omega here, right? Because omega is like a derivative of my barrier connection, of the curl of it at least, right? And that's my P dot here. So basically this anomalous velocity actually tracks the barrier connections that I'm accumulating as my wave packet is accelerated. Right, so to some extent, this anomalous velocity is a way of tracking this anomalous shift that I get in my center of wave packet. And this is responsible for a wide range of interesting things like the anomalous Hall effect, some kind of orbital ferromagnetism, there's a chiromagnetic effect, all sorts of nice, interesting things. Oh, sorry, something happened here. Yeah, sorry, yes. So it turns out that this quantum geometry can also affect plasmons. It can, create some kind of special non-reciprocity at the edges because of an anomalous Hall effect. And people have kind of seen non-reciprocity without magnetic field in magnetically doped topological insulators. When you create kind of a circulator like this, they see that, there's a difference between the left and the right moving kind of propagation signals, even at zero magnetic field. But the thing that I really wanted to focus on was this. It turns out that beyond just the center of the wave packet being shifted, if you change the quantum metric, as Martin I talked about, that contributes to a contortion as well of the wave packet shape. So it can change. It can make it more like a cigar-like kind of thing here, so the wave packet is now contorted. It can also kind of tilted as well. And so you can ask, when will I care about having some kind of tilt or some kind of contortion of my wave packet? And it turns out it's quite easy to kind of see, right? So if I have a homogeneous electric field, and I have just my wave packet inside, my electric field, my homogeneous electric field, should basically only couple with the center of the wave packet. The energy is, the total energy is insensitive to the width of my wave packet, all right? But if I have an inhomogeneous electric field, all right, then basically the total energy of this electron, of this wave packet, will be sensitive to the width of this wave packet. And so basically, by using inhomogeneous electric fields with some finite Q, you can actually now start to detect things to do with the quantum metric. And of course, this is where going beyond the conventional dipole-like optoelectronics towards the nanophotonic type of optoelectronics will actually matter, because you go beyond the dipole approximations, you actually start to look at these spatial variations of electric field. So the key question we wanted to ask was, how does the quantum metric change plasmon dynamics? So it's actually quite simple and quite straightforward. All it really does, this is a simple semi-classical picture. I'll show you an RPA picture in a second. Basically what it is, as I told you, the quantum metric is sensitive to inhomogeneous electric field. So this will now contribute to some kind of energy, right? So as you can see here, there's a partial of R here. So of course, it needs to have some kind of inhomogeneity in my electric field, right? My big E here, right? But that's my energy. How do I get a velocity? To get a velocity, it's always the change of energy with respect to k. So that's why there's a k here, right? And so this is why the quantum metric dipole is the thing which will couple with the inhomogeneous electric field. And as you can see, because there is this derivative in R here, it's sensitive to the direction of the EM wave. So if I have a wave-like kind of thing here with an oscillating electric potential and an oscillating electric field, depending on whether it's going in this direction or this direction, plus q or minus q, this velocity is going to change sign. So clearly, straight away, this will give me an intrinsic non-reciprocity in my system, right? It will now tell me that this thing here was reciprocal, right? This thing here is divergence-free because it's a Hall current, right? So for plasmon, it really cares about the propagation of my electrons. Straight away, you'll find that that we can get a non-reciprocal kind of plasmon because of this quantum metric dipole here that we have. So that's the first thing. Of course, the key point to note is that you have to break significant symmetries to actually get the quantum metric dipole. In particular, you have to break both time reversal and inversion symmetry to have different sizes of your wave packets on different sides of k minus k. And so you have to break both time reversal and inversion symmetry to actually see it. Very quick, 1 minute, I won't talk more about this. If you don't like the semi-classical interpretation of things, it turns out that it really just comes from the overlap integral. And the key point here is whenever you do any kind of expansions, don't stop at the lowest order. People typically stop at the quantum metric order here. If you go one order more to q cubed, you get the quantum metric dipole. And this is the thing which actually gives you something that is non-reciprocal in your for your Linhart function. So this is how you get your plasmon through a Linhart function. In fact, actually, there are two terms when you expand out your Linhart function that give you non-reciprocity. One is the quantum metric term that I just told you about, but there's also one which we call the directional Drude weight, which arises when the velocities are different in either side k minus k, right? But you can see here at large frequencies, the directional Drude weight term here is suppressed. And so going to large frequencies, you can actually suppress this directional Drude weight. You can try to see this, for instance, in a magnetic bipartite chain. And I'm rushing through this part here because I want to get to the intertwined phases of matter part. So there's a 1D magnetic chain. You can see this, and you can just implement everything I just told you in. There's one surprise in it, and the one surprise is that we can tune this magnetic bipartite chain. We can tune these parameters so much so that the dispersion relation is actually symmetric, but it still breaks time reversal and inversion symmetry. So if I stared at just the dispersion relation, I would not have been able to tell that it broke time reversal and inversion symmetry. But actually, it still does. The Hamiltonian does break time reversal and inversion symmetry, but that time reversal symmetry and inversion symmetry breaking is hidden in the wave functions, and it's here, basically. You can see the quantum metric on either side are very different from each other. And in such a case, the difference between plus q and minus q plasmon dispersion relations is given by the quantum metric dipole entirely times the Coulomb interaction. And this is kind of interesting. This is telling you that it's only in the light matter interaction that you can actually see the time reversal symmetry breaking, inversion symmetry breaking of the system. All right? And so you can see, where will I be able to see this in real life, right? Well, you want to kill the directional Drude weight term, which is depending on the velocity stuff, right? So you want to kill velocities. So I want to go to flat band systems, right? So in flat band systems, your velocities are going to be very, very low, all right, very small. And so you would expect actually in these systems, your directional Drude weight or any classical-like terms will not be super important. And actually, it's the quantum metric terms that will be important. So in twisted bilayer graphene, it turns out that plasmons are quite prominent here, and they're actually intrinsically undamped. And a special point of a twisted bilayer graphene at 3/4 filling, there is actually a ferromagnetic state that also breaks inversion symmetry. And so if I dope it slightly into the metallic side, it turns out if I just do RPA, I'll find actually a non-reciprocal plasmon in twisted bilayer graphene on hexagonal boron nitride close to 3/4 filling. All right, so we have this here. And just to confirm that it actually is coming from the quantum side, the overlap integrals, if I set the overlap integrals to 1, just unity, you can see that it's reciprocal. So in fact, this effect is largely coming from that overlap integral part. All right, so this is a quantum effect. You can call this quantum non-reciprocity, right? Coming from the quantum metric dipole. So hopefully this sort of like, tries to answer the question, what happens when I go beyond the dipole approximation? What kind of quantum geometric terms actually start to play into this kind of interaction? It's actually the quantum metric dipole, and it can give rise to an intrinsic quantum non-reciprocity that can be seen in plasmons. All right, so in the remaining 15 minutes, I think, I will talk about the intertwined phases. So, yes.
Sorry, can I quickly ask about the momentum dependence here?
Yeah.
So I would only see the non-reciprocity very close to the Brillouin zone boundary?
No, this is not the Brillouin zone boundary. This is some number we chose. Yeah, it's not. It's not the Brillouin zone boundary. It's not.
So for quite small Q, you would already see.
Yeah, these are largish Qs, but they're not super large Qs. Yeah. So yeah. So that's that. So I'd like to ask the question. So I told you about non-reciprocity. So non-reciprocity is the way of discriminating between forward and backward. In this case here, we have differences between forward and backward, and so that's one way of getting quantum non-reciprocity using the quantum metric dipole in plasmons. But this was coming from an underlying state, a ground state that was already magnetic, that already broke inversion symmetry. So here we had the plasmon of this system, this collective mode of the system that was locked to the face of the metal, as it should, right? So you don't expect the collective mode to have a different symmetry from the ground state metal, all right? But I'd like to ask the question, can I have this non-reciprocity decoupled from the ground state and arise spontaneously? And this will come into the question that Andy asked, all right? So typically when I think of spontaneous symmetry breaking, I think of this kind of Landau-esque way of thinking about it, right? So I change a parameter, change temperature, for instance, and I go from high symmetry state to low symmetry state, right? So this double well appears, very nice, right? And here this is kind of mediated by some kind of exchange interaction. Great. But symmetry breaking doesn't just have to occur in, say, this type of free energy kind of landscape. It can also occur in dynamics. So write down a set of equations of motion, for instance, of x and p of something. And there could also be symmetries of this equations of motion, right? There could be symmetries in these dynamics. And we could also have symmetry breaking in dynamics, right? And so I'd like to kind of convince you, I'll make the claim first. And here's where the intertwined phases come in. The claim is, I take a disk, let's say, of metallic graphene, doped graphene, because I love plasmons, all right? I'm going to shine linearly polarized light, non-chiral, all right? Linearly polarized light, all right? And my claim is that if that the amplitude of that linearly polarized light is large enough, I will start to develop spontaneously either left-hand or right-hand moving stuff. And so here you see that the plasmons here will spontaneously decide to move left-hand or right-hand. And so this is a kind of intertwined phase now of light and matter. The plasmons being kind of hybridized with light.
But may I ask, this is a steady state scenario?
Yeah.
And is there a thermostat or a bath or something? I mean, the normal confusion about steady state illumination is that you wind up at some kind of infinite temperature.
Yeah. Yeah, sure. Yeah, we'll talk about that in a second. Yeah, so.
But basically, I should think that this is steady state, and there's some kind of thermostat to take energy out of the system.
Yeah, if you want. Yes, that's right. We didn't explicitly consider that, but because what we could do is we could suppress heating. So we were basically Pauli blocked from single photon or even double photon transitions. But so it was just basically driving a simple kind of dipolar mode in a disk of graphene. That's it. But we can talk about that in a second. Right. So we call this baryogenesis, and it really comes a little bit from the idea that AC fields can modify band structure and topology. As we know from James, when you shine circularly polarized light on graphene, you can open up a gap, you can create some baryon flux. But the kind of fields that you need are very, very high, right? So where would you get high fields? You might think, okay, maybe plasmons might get high fields, right? Because you compress the mode volumes down. But then you also know that when I change the band structure, of the system, that can also change the plasmons. There's some kind of, topological plasmonics there, right? So there's a feedback loop here, and we want to use this feedback loop. And so here's a simple idea. The idea basically is that I have a dipolar mode of a simple disk, all right, that's coupled in a simple way to a drive, some damping rate, there's some bare plasmon resonance, and importantly, there is some baryon flux. There can be a baryon flux in the system. We just put it in here first for the time being. We'll see that this baryon flux is spontaneously generated. And it measures the chirality of the electrons. And then just make sure that we're walking through this quite well, right? So if there is no Berry flux in the system for the circular disk, the left-hand and right-hand modes have the same energy, all right? So they're degenerate on top of each other, all right? And so if I if I look at the disk response, this is a simple plasmon resonance of my disk, like that. But if I now have Berry flux that's non-zero, then basically this disk response, will now split, all right? So it splits. So my left-hand mode, my right-hand mode are no longer degenerate with each other, right? I want to get to this thing here, all right? So that's where I want to get to. So how will we get there? So the key point is when we shine circularly polarized light on a system, we can generate a Berry flux. In this case here, we're not looking at, we're looking at basically it generating on the Fermi surface. So when you shine circularly polarized light, this basically will count the pseudo-spinners, and you'll basically get some kind of Berry flux that depends on the intensity of the left-hand minus the intensity of the right-hand modes. So the key behind actually having the spontaneous symmetry breaking is nonlinearity, right? And where's the nonlinearity coming from? It's coming from the Berry flux. So importantly here, the Berry flux depends on the total electric field, oscillating electric field that is felt by the electrons. And this includes not just the drive electric fields, but also the plasmonically enhanced electric fields as well, right? So that's the total, which includes the drive and also the enhanced electric fields from the plasmons as well. And as a result, this part of my equations here is nonlinear, highly nonlinear. And whenever we see a nonlinear set of dynamical equations, we immediately expect bistabilities, all right, or multistabilities. Right? And so let me just explain how this multistability actually works. In a simple case here, no symmetry breaking yet. All right, so case one, if I shine circularly polarized light on this system here, and let's put a drive frequency, just below the bare plasmon resonance. It's just below that. So if I shine a little bit of light, some Berry flux will get generated. There's a little bit of a small cusp that gets on top here, but it's still far from my plasmon disk resonance. Right? But as I go even further, there are one or two things that can happen. Right? So I'm far away from my plasmon resonance here. All right? And so I don't get very much Berry flux. OK, that's OK. But my system at this point could choose to actually have a large Berry flux which shifts, which basically splits this resonance a lot, and therefore will shift the resonance very close to my drive. And this actually will amp up actually my response of the system to go more and more and more in that circular direction, and therefore I get a bistability, right? So basically, I'm basically shifting myself. I'm shifting towards my drive frequency, all right? So it's a very simple idea. Basically, I'm here far away from my resonance, and then I shift into the resonance because I spontaneously generated that Berry flux, and then I'm self-sustaining it as well, because now I have a larger response of the system. And it's a very simple idea again. So again, shifting into the drive. And that's basically all I need to do now. Sorry?
This is one of these bifurcations in nonlinearity.
That's right. This is just a bistability. This is just a simple bistability. But now I'm going to use a linearly polarized drive. So if I have a linearly polarized drive is composed of a circular polarized of left-hand and right-hand in equal proportions, right? So at very low drive intensities, I'm not going to get very much of anything at all. Nothing gets so nothing will happen. But at some point, the system can decide, and if I drive now far away from my plasmon resonance, my bare one, it won't do very much. But the system can also now decide to shift again the plasmon resonance into my drive frequency by splitting this mode, right? And this will now spontaneously pick either the left hand or the right hand, all right? And so this is what we call baryogenesis, and this is what we call a spontaneous generation of Berry flux, or baryogenesis, like baryogenesis. That's that. We tried to put in, kind of some reasonable parameters. It turns out that Dima-Basov has very large quality factors in his graphene samples of order 100, so you can put that in. And the kind of powers that you need are not super large at all. They're actually very, very reasonable. Maybe there are some overestimates here of how good the quality factors are, so you can take some factors of 10 off, and still, it's still very, very reasonable powers. But I'd like to kind of emphasize that this is a different kind of magnetism, right? So it occurs as an outer equilibrium excited property. and doesn't really require spin. Spin is a spectator degree of freedom. And it's quite different from this kind of Landau West kind of way of thinking, right? So here I lower the temperature. In this case, here I increase the plasmonic drive. And I basically go from having this being my fixed point here, 0 Berry flux is my fixed point, to having a bistability here, and having these two now, this becoming unstable, stable, stable. Finite Berry flux is my fixed points. So it's a kind of a different kind of a magnetism kind of way of thinking about things. And that arises from an intertwining now of that plasmonic phase and the light phase. So that's why I call this an intertwined phase of light and matter. All right, so with that, I stopped for questions before time, I think. The key kind of take-home point is that there can be intertwined phases of light and matter, but plasmonic non-reciprocity can be quantum. All right, this arises from the quantum metric dipole. All right, and you can get this some kind of spontaneous chirality from this kind of baryogenesis way of thinking about it. And that's actually a very kind of general mechanism, right? It's just shifting of resonances, right? So it's not anything like super technologically advanced. You just move the resonances up and down. So it should be robust. And so with that, thank you very much.